So we are video recording, and where it is? Yeah, and I see the faces of somebody. Okay, so let us complete what we said at the end of the last lecture. So I want to prove that f is a vector. So one has to understand more precisely, this is a statement for shocking people following the lecture. So what I do, I write f of v like fi a v a e i. This is the first formula written here. Okay. How do we get this? We get this by writing f of v equal, we use linearity. So I write v as a linear combination of capital E A. VA gets out here. Okay. And then as final step, I represent F E A as a linear combination of small ei, and I replace it here. Then reorganizing with associative and distributive properties, I get the final formula for the vector fv. So remember that fv is a small vector. So it belongs to the space of displacements. Okay. Then I rewrite fv in the new basis ej prime. Okay. And I don't repeat the calculations. I get that fv is equal faj. So I get this. I adapt the previous equation with the new basis ej prime. Then I transform ej prime in the basis, in the old basis ei. So here I write here, I wrote it quickly because I have the habit of doing this now since many years. So I write this and I replace it exactly here. Okay. Now, as I have two vectors, fv equal fv, and I have represented, which are equal, and I have represented this same vector in the basis ei in two different ways because of unicity of representation of a vector in a basis. Then for every I, this equality is true. Okay. So I reorganize the equation, placing everything on the left. So I get this equality. And so I know that for every A, this equality to 0 is verified. As we will repeat this reasoning many times, and it is crucial for the minimization and stationarity conditions, which we will consider later, I repeat once more the argument. So I choose the particular VA like this, so that the previous equation becomes this. This is the delta, which is 0 and 1, depending if A is different from B or A is equal to B. And as a final, result, I get the formula which we wrote yesterday. So we discover that when I transform the basis, so I change the basis in the actual configuration in this way, the components of F are transformed in this way. The upper index is transformed as a vector. The upper index transforms as the index of a, let us say, Eulerian vector. You know, we have the reference configuration, sometimes is called Lagrangian configuration, and we have the actual configuration, which is also called Eulerian configuration. Okay, so sometimes I will say Eulerian, sometimes I would say actual, sometimes I would say displacement or displacement vector space equivalent. So F is a vector in the space of displacement. So it is contravariant when we consider the index, the small index I. Okay, so now you have understood. So I will ask you to do some calculations and prove that this is true. You must repeat what we did now, simply changing the basis EB into, okay, maybe it is better if I help you a little bit, EA into prime, and you will get this same result, so that you discover that F is a covector in the change of Lagrangian basis EA into EB prime. Okay. Very well. So now we must generalize. So let us do the generalization. I was thinking how to do this generalization. So I decided that we did it up to now rather slowly, so that we can do it quickly. So I will define for the moment, I consider only the space VB, the vector space VB. Then we can consider many vector spaces. Okay, maybe it is worth that I open a little bit a bracket here. What we did, we considered C, which is a map from VB into VB. So is a linear map from one vector space into itself, sometimes using the Greek word, we call this endomorphism. Okay. Or we considered F maps VB into VS. So we are ready to consider, we know, if you like, we must accept that our linear applications can be defined in the same or in different vector spaces. It depends on the situation. Okay, so in the generalization which we will do, we'll use different vector spaces. But for the moment, let us consider something which is defined in one and the same vector space. So every vector space for the moment is the same, VB. So for every basis EI in VB, okay, we consider a set of numbers as follows. L, E1, E2, EK, J1, J2, JH. I understand that this can be difficult, but we need a double indexing. I understand the difficulty. Okay. Why? Because we are obliged to do this. We are obliged to do this because we don't have enough letters of the alphabet. You know, in English we have, now I always forget, because in Italian we had 21, then we added others. I don't know, maybe in English we have 26, but whatever it is, in Russian they have 32. I mean, you don't have, you can use English and Greek, Latin and Greek letters, you can do many things, but the problem is that whatever you are doing, you will never have 100 letters at the top and 200 letters at the bottom. I mean, whatever it is, we want to have free hands in considering K upper indices and H lower indices, where K and H are generic natural numbers. Okay, so we need to introduce this notation. So you have I1, I2, IK, then you have J1, J2, JH, okay? Each of these indices, I1 runs from 1 to n, VB has dimension n. Okay. Also, this J1 runs from 1 to n. So, sorry, but I alpha with alpha between 1 and k runs from 1 to n. So you have a double indexing. The small index labels the index, and when you have one of the indices, I alpha, this index runs in the set 1n. Okay, and similarly, you have j beta. Beta runs from 1 to h, and j beta can have the value 1 up to n. Okay. To each of these, this is what we can call a multi-index. I need to separate the two kinds of indices, so I place a semicolon for dividing them. Now, to each of these, for each value for this multi-index, I associate a real number, which, following the tradition of Levi-Civita, I label in this way. And this is a real number. And I associate different numbers when I've chosen a different basis. Okay. Now, this is a generalization of what we have already done for CAB. Okay. Because CAB, which is F transpose F component AB, is a table, a set of numbers associated to the pair of indices AB. Okay. Now, when we consider FEA, we have indices coming from two different vector spaces. So we will need to be more careful when we are considering different vector spaces. Why? Because we will need to fix the basis for each of the vector spaces with which we are playing. Okay, so it is clear that we are trying to generalize what we did up to now. Okay, now let us consider this Li1 Ik J1 JH. Okay, and let us saturate I1 V. Okay, VI1 is a covector, the components of a covector. VI2, VIK, okay? And these are all components of a covector. And we introduce Vj1, Vj2, Vjh, the components of a vector. Okay, now let us be very careful. In general, this is a vector, this is another vector, so we must invent a notation. So Vi1 are the components of a vector, covector. Vi2 are the components of another vector. So the covector. So the difference, you know, the poor index is carrying also the notation concerning the vector. Actually, one should write V1, V2, VK, V1, V2, VH. Okay. And in general, we have different vectors, and we are considering the components of all these different vectors. Okay, so I will try to keep this heavy notation, but always consider that when I change the index structure, I am changing also the vector exactly as we did for EI. And when we wrote EJ prime, sometimes in the literature you don't find E prime, J prime, because when you write EJ prime, I mean, this was this abuse of notation. I don't know you, but for me, as a student, was very difficult to understand, because nobody explained me this openly, clearly. So this is the reason for which I'm telling you every time, because for me it was a nightmare. You understand that if you interpret this literally, you simply changed the name of the index. The basis is the same. You know, what is crazy? In some books, you find a long explanation about dummy indices. They explain you that you can change the name of the index. So finally, you accept it. You are happy, and then they write you E, J prime, and you believe it is a dummy index. Okay. So you believe that you are dealing with the same set of vectors, and you simply changed the index. In reality, we are changing the basis, and we have E prime, another set of vectors with its own index. The abuse of notation of skipping the prime here and writing EJ prime is very convenient for writing quickly the formulas, but you must be aware that when you label the index, you consider as labeled also the letter to which you are attaching the index. Similarly, this is the case here. Okay, so I will not write this index here, but it is considered there, and it is related to the sub-index for the indices I1, I2, IK, J1, J2, JK. Okay, so I hope that I did clarify a point and I didn't confuse it. So let us consider L, I1, I2, let me be consistent, IK, J1, J2, JH. And we are saturating with VI1, VI2, VIK, VJ1, VJ2, VJH. What we get? A real number. Okay. These are components of a covector, and these are, look, this is ambiguous. These are the components of covectors, because I told you that they can be different. And here I write, I consider the components of vectors. Okay. Very well. If the found real number, let's call this number alpha why I want to underline that alpha EI depends on the basis EI chosen. By the way, I open a small parenthesis, then I repeat everything for you. This is the definition found in Landau, the famous book of theoretical physics, or in Feynman. Okay, another famous book in theoretical physics. Mathematicians prefer another equivalent definition, which we will discuss later. Okay. So I prefer to tell you a definition, probably simply because I am a physicist. So I have this mental disorder, if you like, but I think it is more meaningful with respect to the mathematician's definition. By the way, the definitions are equivalent. Okay, so let's go back and repeat slowly what we are doing. We consider a set of numbers as follows. For every basis EI and VP. So I have a basis EI, and for this, to each basis EI, I associate this set of numbers. So how we consider this set of numbers? To every choice of the indices, k times up and h times down, okay, I associate a number. So this is a function in reality, okay? So it is a function that for every EI and for every E1, EK, J1, JH, I associate L, E1, EK, J1, JH, and everything depends on EI also. Okay. Okay. Then what I'm telling you, I consider this number, alpha EI. This alpha, of course, depends also on the vector V1 of the covector V1, big F with indices always. V1, Vk, and the vectors V1, V2, Vh. Okay? And this number is obtained saturating one by one the indices. Every index up is saturated with every index down. Okay? Now, if the found real number, this one, does not depend on the basis, what it means that alpha of EI is equal to alpha of E prime J prime. So you change the basis and the number is always the same. Of course, remember that these V components and these V components are changing in a known way. So recall the components of covectors V1, Vk, and vectors V1, Vh are varying as they must vary. Okay. Okay, so when this number does not depend on the basis, then we say that L, I1, K, J1, JH are the components of a tensor. The tensor Li1, Ik, J1, JH is H times contravariant and K times contravariant and H times covariant. Okay, so this is a definition. We can say the definition by the physicist. A vector is not a vector in the Eulerian space is not three components, three numbers. A vector is a choice very carefully determined for every basis. I get three components. When I change the basis and the arrow is always the same, I change the basis, the three components change, but they are not changing as they like. The three components are changing following the contravariance rule as we calculated. Okay. To generalize this concept, for every basis EI, I choose this set of numbers. This is a tensor when the saturated number which I've written here does not depend on the basis. Now, which is the definition of mathematicians? I take VB star, Cartesian VB star, Cartesian VB star, K times. So I have every K ordered set of covectors. Cartesian VB, Cartesian VB H times. Okay. A tensor wait a second. Maybe I'm using the wrong order. No. Okay. A tensor is a linear map from this set, let us call it how can I call it? W into R. Okay. Now, what I want to do before the end of this lecture is to prove that these two definitions are equivalent. So we are talking about the same object. The same objects. Okay? So mathematicians and physicists are looking at the same mathematical object from different points of view. In a sense, mathematicians are synthetic. Synthetic in Greek means to have a unitary vision, okay? While physicists are analytic. They want to describe into the detail the concept we are dealing with. Okay. The idea of a physicist is you give me an observer, therefore you give me a basis, and I want to know the numbers associated to your physical quantity. So think about once more deformation, CAB. I choose a basis and you give me the numbers associated to this basis. Okay. While the mathematicians think in general as the effect which these numbers have. So talking about deformation, what is CAB? CAB is the inner product of EA to C applied to EB, the inner product VB. Okay. So let us invest a few minutes about this. If you remember this definition, this is also equal to FEA, FEB in V small. Okay, so what this means? If A is equal to B, this is FEA inner product FEA in VS. So you have a vector EA, you have its image FEA, and this is the length. So this is the norm square of FEA. So this number is telling you how the initially EI is of length 1, imagine. So you have an initially vector having length 1, and you want to know how it is elongated. So CAA minus 1 gives you the elongation of EI under the map F. And you understand that for a physicist and for an engineer, this is very important because I want to know how one vector is elongated. If A is different from B, you get FEA inner product FEB in VS, and we know that this is the norm of FEA, which we already calculated, the norm of FEB, which we already calculated, cosine of FEA FEB angle. So this number gives you how the angle, we assume that at the beginning it is orthogonal. So you have E1, E2. Then you have F E1, F E2. They are elongated, but also you have an angle, which is not pi over 2 anymore. And this number, CAB, gives you exactly how the angle is after the deformation. So if you are an engineer or a physicist, you consider more important to discuss about the components of C, because you attach to these components a physical meaning. Instead, if you are a mathematician, you want to underline that deformation is a linear map. The linear map, which maps every vector V in another vector W, they are all Eulerian. Okay, and this C allows you to calculate every inner product between V1 and V2, every pair in the big inner product. So in a sense, this symmetric linear application represents a new inner product. So if you are a mathematician, you will say that deformation is a change of inner product. Okay, and this is your synthetic analysis. Okay, very well. Now, let us prove that these 2 points of view, not only in this example, are exactly the same. And this is very important because you must learn how these concepts. Okay. Okay, so let us start with the definition of mathematicians. I have L, and I apply it to V. So the first are, in our notation, the first are covectors. So V1, V2, VA, and then I have V1, V2, VH. Okay. Okay. Should I prove that this quantity does not depend? This is a real number. Should I prove that this number does not depend on the basis? No. I never thought about a basis. L is a linear map. defined as it is defined, I take vectors. I'm not talking about components. So this is a number. This is alpha of V1, Vk, V1, V2, Vh, independent of the basis. Okay? So I already know that this quantity is independent of the basis. Okay? Then I write L and I start writing the linear combination of my vectors. So I have V I1 E I1. Please don't forget that this is the basis of covectors. Okay, and the basis of covectors has the index up, while the basis of vectors has the index down. The only covectors which you must denote with an upper index are the bases, the elements of the basis. Okay, this is the crucial ingredient of the convention we are having, we are using. Then you have Vi2 E I2, Vik Ik, semicolon, and then you have Vj1 E J1. This is the basis of vectors up to Vjh E Jh. Okay. By definition, this is a multilinear application because we defined, okay, I didn't say multilinear, but I mean multilinear, of course. So where it is? The definition is a multilinear map. It is linear, I mean, it is linear for every vector component. It's not very happy. Every vector argument. Okay. So here, very carefully, what I do, I write Vi1, Vi2, Vi dot dot Vik, Vj1, Vj2, Vjh, L of I1, I2, I.
Haşık gibi. Sorry, Professor. In the other side, last VJH, EJH, was it supposed to be EJH, not K?
You mean that in my convention, I wrote here H and here K?
No, upper side. The below independent of basis, right? So you wrote VJH, EJK. Denetim isteği gösterebiliyor muyum?
Okay, I don't understand what you're telling me. Tell me exactly another time.
So the line you wrote, L, Vi1, EI1, Vi2, EI2. Yeah.
Which one?
Yeah. And the last thing you wrote, VJH, EJK. But was it supposed to? Okay, H. Okay. Thank
Okay.
you.
Thank you. Thank you. Now, okay. Please be careful because it is impossible with all these indices never to be wrong. Okay, so you know, I prefer to write while I'm telling you, even if I risk to be wrong sometimes, because in this way I'm not running too much. So I think that it is better to be wrong sometimes. You are careful and you correct me than having everything written since the very beginning. So now remark carefully. This is what we are doing. And therefore, if you define L I1 IK J1 JH as L of E1 EK EJ1 JH. This is a definition now. You get L I1 IK J1 JH V I1 IK V J1 JH equal to the alpha independent of the basis. Okay. So what we have proven? We have proven given an L multilinear defined in W. I know it is confusing, but okay, let's call W tilde. I mean, we emphasize that this is the set of K covectors and H vectors given an L multilinear defined in W tilde, we have a unique tensor whose components for, let's say, in every basis are given by this formula. So I write that L I1 IK J1 JH is equal. This is a definition because that what we have on the right is well defined. A E1 EK IK E J1 JH. Okay. So from the synthetic definition by the mathematicians, we get the definition by the physicists. Okay? Now we must show that the vice versa is true to show the equivalence. So for every EI, we have L, I1, IK, J1, JH. Okay? Now this is even more simple, but let us understand this. So definition, L of V1 index now, otherwise it is a disaster, VK, V1, VH is equal, by definition, now I am defining the linear map, it is equal to L, I1, IK, J1, JH, V, I1, VIK, VJ1, VJH. And this is a real number. Now, the definition of physicists tells you that this number, alpha, is independent of the basis. So this definition is well posed. It is a real, it is a true multilinear application which maps vectors into real numbers independently of the chosen basis. Okay, so it is trivial that the 2 points of view are exactly the same.
Sorry, Professor.
Yes.
Alpha is equal to L, yeah, LE1 to EK, G1 to GH. You wrote GK.
Yes. I am not, you know, okay, let us stop and comment a while. Because of these indices, one must check carefully while writing formulas. There is a group of mechanicians, of experts in continuum mechanics, we will call the Truesdellians, who claim that they can avoid to handle indices. So in the by Truesdell and Toupin. Toupin was a very clever guy whom I met before he died. You find indices, and indeed you understand everything it is written in that book. Then Truesdell wrote a Truesdell null book, and null decided to cancel indices. The result is that nobody knows what is written there, or it is very difficult to understand what is written there. You know, when this notation, we will go back to this point, this notation is telling you exactly what index is saturated with what index. Okay, and you cannot be wrong. If you write L, V1, V, VK, V, I mean, in the right order, V1, okay, imagine that you are stupid and you take away every index and you write L, V, W, and then for covectors you use small letters. So you can use, following some notation, VW, VW, for having a fourth order tensor. You don't know which index is saturated with which index in your calculations. And this could cause a total mess in the reasonings. So even if I agree with you, systematically you must check what you are writing in order to be sure that you didn't forget something. You cannot avoid using this notation because it is extremely precise. And in reality, when you want to place, let us use this metaphor. You want to place every atom at their place because you want to be very precise. You risk to place an atom in the wrong way, So you must be very careful. However, the notation by Levi-Civita is self-correcting because you have some rules. And when you discover, as we did yesterday, that you are wrong in placing the index, you have immediately a terrible incongruence of your formulas. And so at the end, you discover the mistake which you did. Okay, so I think that for the moment, we can consider the part of covariant and contravariant tensor algebra. We can consider this part completed for our aims. Now, remark, we have some minutes, so we can do something. Remark, we never used the inner product structure in VB. Up to now, we have only used linear combinations, and we defined the dual V star B as the set of linear applications from VB into R. Think about it. We never introduced in our reasonings the inner product, except as an example. Okay? We used inner product simply as an example of bilinear application. Okay. You remember we did already one time. I want to do it now for preparing next subject, what is called Cartesian tensors, where inner product plays a role. So we we will consider in the next lectures VB, an inner product in VB. So we will consider a more complicated structure, and we will see how the tensor algebra is simplified by the inner product. Okay? However, I think it is very important to talk about tensors without inner product. The reasons are: one must use the minimum structure which is possible. This is clear. If you introduce too many ingredients in your reasoning, you are confused. Okay? And second, one must immediately see the difference between vectors describing displacements and covectors describing forces. Let us think about this. You know, Galileo, D'Alembert, Lagrange wrote a lot about this point. So let us stress this point before we end. A displacement is a vector describing how we can move from a position P1 to a position P2. Okay? This is a displacement. By the way, we are measuring displacement. Okay? Then we talk about the work done by a force on a displacement. Think about it. It is the work is a linear map. Let's call displacement U. It is a linear map which associates to you a real number. The true nature of a force is this one. A force characterizes the amount of energy which is transferred or taken away to your material particle by the agent acting on it. Okay. Nobody never measured a force. Directly. Think about it. What is a dynamometer? You take a spring. You load it. You have a needle. The needle is 0 here. Then you load it. The body goes down. The needle is there. And you measure what? A displacement. Or you have a body which is moving. You know the mass of this body. You calculate the acceleration of the body. So you consider 3 positions in 3 different instants, very close. And you measure the acceleration. Then you write F equal mass times acceleration, and you estimate the force applied. So statical forces and dynamical forces are all measured by using displacements. So in a sense, VB is the fundamental set of vectors. We can have access to them. V star B is a super structure. It is a logical construction. Nobody can access directly to forces. Okay. So what we believe, what the school by Lagrange and followers believe is that the basic foundations of mechanics should use the space VB and not the space V star B. Okay, but this we will discuss in the next lectures. So I think, Alessandro, we can switch off the video, and it is 10 o'clock.